a software engineer at QuillBot, and Ashish, who's the platform engineer at QuillBot, with us. So we will be taking a session on containers at scale, where he would be explaining regarding the Docker, Kubernetes, and stuff from the very basics.
So are we good to go? I'll just share my screen. I have PPTs. So
Yeah, yeah.
let's see.
Yeah, Ashish, I guess you can share your screen, so I'll start.
Yeah, my screen's visible, right?
I'm trying to see it. Yeah, screen is visible, I guess.
Yeah.
Can you shift to the slides?
Yep.
Because I think there is a different window that is pinned because I'm also the presenter. That is why showing me. Anyways, so hello everyone. So today, me, Siddharth, and Ashish have connected to give you a small talk on topic which is containers at scale. And first of all, I would like thank you. I would like to thank everyone for joining today, that too on a weekend, and specifically thank you for introducing me and my colleague. Okay, Ashish, maybe you can start and maybe you can move to the next one.
Yeah.
Uh, yeah. Okay. Okay. So, firstly, we'll talk about what is containers, why containers, and so I've tried to make the introduction very user friendly. Try to keep the language as simple as possible so that everybody is able to relate. So it's the intro part is basically kind of fun. So maybe if you can try to focus on the screen and try to read it, the screen that is being shared, you will find what exactly I'm trying to say. So if you can see, the joke that I'm trying to convey is basically there are two people who are having a conversation and saying about there is a piece of code or application that is working on a particular machine and it is not working on the other machine, and the other person is telling, okay, then we'll ship your entire machine only to the client. So that is where the containers were born basically. So the primary reason why we are calling them containers is because there can be a shift of environment, as simple as there are two people that have or work on different OS versions or may have different kind of applications installed on the system. So there might be a possibility. So let's say there are two developers working on the same code, and there is a possibility that that particular piece of code you have a some different dependency version present on your machine, and the other developer has different version dependency present. So they can cause a conflict. So because of that, just to ensure that everything works like seamlessly and smoothly, irrespective of the environment that you're going to be in, like it can be any OS or irrespective of, just to finalize the dependencies and everything, we created containers. And as the name suggests, the containers is basically trying to contain something, which is like your entire dependencies of your project, your entire application code that you're going to package it all together in a single package and then ship it across, or maybe like deploy at multiple locations to facilitate your entire application that is exposed to the client. So what exactly happens is when we bundle up, what are the exact benefits that you are getting by making it or shipping it in containers is, so first of all, our development speeds would increase. Then we can do any kind of, let's say there is a bug or any kind of code that is supposed to be rectified and it needs to be shipped immediately and changed immediately, or like some kind of a patch is supposed to be applied, it there can be great amount of speeds. And because of the urgency of the matter, let's say your application is client facing, so it's important that we have dire speed and high speed basically to rectify it. So all these things you will get in when you're using container. Ajish, can you move to the next. Ashish, can you move to the next slide?
Yeah, is it not visible? Like I
Yeah. Okay.
moved it. Yeah.
Everybody have might have seen this particular meme, this video floating around, where two people are fighting for the space in a bus, right? So here I'm trying to relate about the scale basically. What is the scale that I'm talking about and why it is important? So basically, as engineers, we work on some specific piece of hardware or devices, and each device has a specific computational power. Okay, so let's say given let's say a particular machine or a particular device is able to support 100 users and you have a throughput or an input of 200 or 300 users, you need to basically replicate that particular machine, so that you need to add up basically more machines to your entire infrastructure so that you can scale and serve that much amount, basically scale and serve that much amount of audience. So that is why it's important that we realize at what scale our application is going to perform, and in simpler terms, how many people are going to be there in terms of traffic who are going to use it live. Can you move to the next slide?
Done.
Yeah. Okay. So if you read the meme again, so it's like there is a conversation between a teacher and a student going on where they are talking about the network issues and the traffic, and the teacher is not trying to believe it. So it's like, if you recall, everyone might have gone through this. Like there used to be a time where we used to go and wait for the big billion day sale of Flipkart to happen, right? And suddenly you see that their entire site used to crash at times, right? Everyone might have gone through that, right? So basically, in such scenarios, scale is important because you need to analyze your data, that what is the kind of traffic and what volume of traffic are you going to expect. Okay, for example, if you are assuming that, let's say, you're going to run some kind of a sale campaign or something on your website or your application, or maybe on some festive reason or any something, uh, it's important to pre know the volume of the traffic so that you have proper instances, proper containers deployed and scaled up so that it can support that much amount of traffic, because traffic is going to be splitted across these particular containers. Okay, so that is why scale is very important, and we have few strategies to uh, talk about or decide how we take right or proper decisions as per the industrial standards, so that you have your application running in a smooth flow. So first and foremost, I can just give you a simple example of which is very rudimentary in terms of nature. It can be as simple as that you can have a simple check on your machine which tell you like how much RAM and how much processor is occupied, and on the basis of that, you can immediately scale up a new or spawn a new instance or a new container that serves the rest of the traffic. So it's like, let's say your application is serving 100 people as of now with 80% processor occupied and 90% RAM occupied. You immediately spin up a new container so that the next 100 users are going to be diverted to the new machine. Okay. Ashish, can we move to the next slide?
Done.
So now basically I'll make you visualize why we call containers just by, I want everyone to basically focus the image. And if you clearly see the picture, you can see containers on the right side. You will see a fueling station. You will see a small building on the left side. That can be a management building. And then there is a ship basically that is supposed to carry the containers. Okay. So everything here has a crucial role to play. So containers, as I told earlier, it's used to bundle up your entire application, your software, your code, and anything that you're going to expose to your client, and they will be using it and using your services, whatever you are providing. Why ship is important? Because, so I'll give you a classic example. Let's talk about Netflix a bit. So everyone knows that Netflix is a OTT platform. It performs content-rich content like movies and TV shows and everything. But imagine, let's say if Netflix will have all their servers located in US only. So there is a huge amount of geographical distance from India to US, right? So in that case, the major problem that comes in with respect to the network is latency and throughput. Okay, so for content to be streamed from servers located in US is to India basically would add on to the latency overall. So what Netflix does to that is Netflix basically ties up with your ISP providers and install their servers there locally, and basically all your TV shows and everything is basically downloaded on those boxes via cloud, and then your TV shows and your movies and everything is basically streamed from your ISP provider itself rather than from the servers that are stored in US. So your overall latency decreases and people are actually able to watch the content without a lag. So shipment is important because you need to have at times, according to the audience you're trying to cater to, if you have trying to cater audience worldwide, you need to have different data centers and different servers at different locations. So let's say there is an Indian server that is probably located in Mumbai region of AWS or Google Cloud or anything that is catering to the Indian audience only, and then there is a separate server that is catering to the US audience likewise. Okay. Then if we talk about the building, so building is kind of the orchestrator or the manager that is going to have people who are going to manage the shipment. So it's like orchestrator and manager are going to uh, take care of few things. First and foremost, like if we talk about exactly in terms of containers only, let's say you have shipped your container worldwide. Okay, you need to know whether the containers have reached their specific location properly. They are running in good manner, they are performing well and everything. For all these things, you will need an orchestrator. So basically, to know if your device is not working properly, the orchestrator will be communicated, and so that your application does not go down immediately, a new instance would be spawned so that you know that okay, my application is running fine, and this is the particular piece of code that was buggy, and you can immediately fix it so that not all your containers go down immediately all at once. Okay, so that is the work of the orchestrator. So overall, this picture summarizes what we have in terms of DevOps, how we scale everything, how we cater to such a huge amount of audience. So I'll just give you a gist. We at QuillBot basically cater to almost 60 million audience daily active users basically. And that and just to give you a rough idea in terms of amount, our monthly billing of just the instance is close to 3 to 4 lakh dollars, which sums up to, in terms of INR, close to 25, 26 crore rupees. Okay, so that is the amount of scale that we are talking about. So why scaling is very important, why containerization is very important, you need to know, have a gist about it because it's a really interesting stream. You can take this up as your further career choice, and you can learn a lot of things because development is one part, but taking the development to a huge amount of audience is an entirely different journey. Okay. Okay. So I'll hand it over to Ashish now. He'll talk you through the technicalities here, like what all services, what all options we have for deploying containers at scale. And all over to you, Ashish. Thank you.
Thank you so much. So, guys, I'm audible, right?
Yeah,
Yeah,
you're
you're
on.
audible.
Yep. Awesome, awesome. So, yeah, next up, what we'll try to do is we'll try to decouple how cost. So, these intelligence you need to have on your system, you need to have on your Kubernetes itself, so that you scale up and scale down according to the requests coming. Otherwise, it'll be very, very costly. And down the line, I'll tell you like why exactly are we so concerned about cost. But yeah, for now, you can think of the Kubernetes system in a pretty small diagram, like constrained very small diagram where you have the controller actively looking for pods and you tell the controller the rules that you want to apply, so say CPU or a RAM usage, and based on the rules that you give, the pods will auto scale or scale down, scale up, or whatever you give. So suppose the RAM usage is less, it'll automatically scale down, and if it's more, it'll scale up. So our definitely de facto solution was using Kubernetes. So the next thing we did was we wrapped everything in a Kubernetes cluster. So in the previous slide, what we did was we added a CDN to the server. Now what we did out here is our web app backend and ML models are wrapped all in a Kubernetes cluster right now. So everything is running in a cluster. We have auto scaling well in place for all of these. And what exactly extra we did out here? Okay, so if you see the dotted lines out here, we what we did was we created a VPC cluster. So what exactly that means? Okay, so if you go back to the previous diagram, all the web app backend and ML models had their public IPs. So there was no single point of entry for the traffic. So ideally, what we would want is we would want all the traffic to come inside through a single entry point and go outside through a single entry point. Now, I do not mean to create a choke point. We use a pretty heavy load balancer out here. But what I mean out here is all the traffic coming inside our servers have a single IP. So what this enables us is we can monitor the incoming traffic pretty heavily. So what type of users are actually hitting us? Is it a DDoS attack or not? And in case of anything malicious happening in the system, we know which exact point to target to. We can go to the public IP while a load balancer. We can see what were the incoming traffics, what were the outgoing traffics, and we need not worry कि कहीं और से traffic आ रहा होगा कि नहीं आ रहा होगा. So that all thing is enabled by encapsulating everything in a VPC cluster and putting it all behind a private IP. So it's the same kind of experience that what a router does for you. So you have all your machines connected at your home, and they all have their private IPs, and your router exposes a single public IP to the world out there. So all if you go on your devices and check the public IPs of all your devices connected to a single router, everyone would have the same public IP, and it's your router's responsibility to route the packets where they needs to be done. So it's the same kind of setup we have out here. Whenever a request comes into the public IP, we check in the route parameters and the headers, and we route the request accordingly. Any doubts up to cool? I guess it was okay. So now coming to the most important part, right? So how exactly running Kubernetes for our normal applications is different from running your GPU containers on Kubernetes. So how exactly it is different, and it is really hard or not? So we'll try to deep dive into that. So there are few problems that we face when we run GPU containers, and especially at the scale that we are talking about. So out here is a log snapshot from our ML instances. So what you see out here is zone resource pool exhausted. So we are a very, very heavy NLP based company, and what often happens is when there is our peak loads, Google is not able to cater to the request, the GPU request that we have. So that is something that you face, and especially now we have GPUs at a very scarce resource. GPUs are a very scarce resource, and especially in the region that we operate in, and you'll often find these kind of errors popping in our system where Google is not able to cater to the request that we have. So what we have done to solve it basically is we have went multi-cloud. So our ML models operate on Google, AWS, as well as Azure. So what basically happens is if one cloud provider is not able to serve enough GPUs to us, we move to the other cloud provider pretty seamlessly. So it's pretty cloud agnostic system that we have designed out here, and we have to do it quite often, especially with the traffic coming back now. So yeah, that's one thing. And the other thing is bulky image sizes. So if you create a traditional Docker container, right, it's pretty much 1 GB or 2 GB. That is pretty much easy to scale. It takes about 5-10 seconds maybe at max if you have a good internet connection on your servers to scale up and download everything and run. But running ML models is pretty hard. The ML models, the Docker images that we have goes to north of say 40 GBs, or some of the models are 50 GB and 60 GB too. So unlike web app or REST servers that we have, the front end and the back end servers we have, we cannot really expect real time scaling for our ML models. We had to do something. So earlier we had a load time of about cold boot time of 30 minutes or so. So we had to find something like what exactly to be done. So that's two main drawbacks of running GPUs at our scale basically. So, and let's see what we exactly did. So first of all, if you go back to the previous slides that we had, the backend and the ML models, they were communicating with each other in HTTPS. So now the drawback to that is, the backend server waits for an ML model to call, and if the ML models are busy or maybe scaling up, all the requests gets bloated on our backend system. So the immediate thing that we need to do is we had to have some queuing mechanism that we had. So like it's same as the data structure that we use, uh, stacks and queues, wala queues. So what the backend server now does is it immediately sends all the requests to the queue. Everything is pushed inside the queue, and ML models process it aram se. So some of the sentences might take long time. Some of them might take 5 seconds, 6 seconds to process. Our average latencies are about 200 to 300 milliseconds. But sometimes if there is a scaling problem going on, like I said earlier, maybe there's a zone pool exhaust in a particular cloud provider, or maybe the ML models are still scaling up. So in that cases, what might happen is we might not be able to process your request in real time. So what we exactly do is we take all your sentences that you give, we push them all in a queue. The queue has everything waiting, and whenever the ML model spins up, it'll take something from the queue, it'll just pop something out from the queue, and it'll send back the request to the backend server whenever the processing is done. So that way we have a buffer of in case there's a load spike or something, our ML models will not go down due to the overwhelming of API requests from the backends. Everything will be stored in the queue, and ML models can take their time to exactly scale up and stuff. So now that still leaves us with the question where, like, the ML models are taking 30 minutes to scale. So we do not expect anyone to wait for 30 minutes to paraphrase one sentence, or maybe grammar check a paragraph. So what we exactly did out there. Okay, so yeah. So now if you like, uh, you know, kind of dig deeper into Docker. So what Docker basically is a set of instructions. What Docker calls it, what a container calls it, a layer. So you have different type of layers in your Docker images. Like you can see out here, it's the open source Locust Docker image. So we have different layers which are individual commands out there. So if you read this Docker image from top to bottom, it has a command that whenever the Docker image starts, you have to call this particular command, and you have to switch to the user locust, and you have to run this command, these kind of stuffs. So these are individual layers. So just like the CDN thing that we have earlier, what we exactly did in our Kubernetes part was we cached each and individual layers on our network itself. So our ML models that were taking say 30 minutes or so to spin up, now that we have the layers cached of the ML model in the system itself, like in the network itself, the boot up time decreased from 30 minutes to 6 seconds or something. So that was the impact of caching that we had. So ideally, this is not what we would want. We would not want anyone to wait for 6 seconds only. We try to keep all our requests at 200 milliseconds or so. But yeah, it still was a huge improvement from the 30 minutes cold boot time we had earlier. So we are still improving on it, but yeah, that was a pretty big thing. So, any questions on the ML part, especially? I mean, this is something that not many other companies operate in, and yeah, I think it was interesting. Okay, cool. So now we have a pretty resilient architecture. We have everything contained as of now. We have the if you talk about the architecture from the left hand side, we have our front end servers which are caching all the payloads on the CDN, so user are pretty much able to uh, you know visit our website with very low latencies. And then we have our REST servers that the Kubernetes orchestrator is looking at. So whenever there's a huge spike of requests, the Kubernetes orchestrator will scale up our REST servers. So we have that in place. We have a single entry to our cluster. So even if there's a DDoS attack or something, we exactly know that where exactly the traffic is coming from, and we can block the user from the entry itself. There's no other way that the user can enter our premises. So we have that in place too. And now we also have the queue in place with the caching system that we have. So yeah, everything looks pretty resilient. It's just one thing that we are forgetting to miss out. It's the outbound traffic that we have. Now, why would we exactly want to monitor outbound traffic? So like every project, we also depend on a lot of open source code. So if you talk about the stack that we have, we use Node and Python probably, primarily. So we have a lot of open source Node packages out there that we use. So although we do a intense image scanning of all these before pushing it to production, there might be some cases, some vulnerabilities that might not be identified as of now. So what we exactly do is we need to monitor the outbound traffic from our pods too. So suppose there's a malicious code and that is sending your research paper that might be winning a Nobel Prize or something to some third party services. That would be a pretty big deal breaker for us. So we need to monitor all the outbound traffic too, as well as the inbound traffic. So our single point of entry was able to monitor all the inbound traffics that were coming in the cluster, but they want any checkpoints to exactly monitor the outbound traffic. So we needed something in place. So what we exactly deployed was a service mesh. So a service mesh is a normal concept. It's a pretty widely used concept. It's getting famous in the DevOps and the Kubernetes as well as the security community right now. So it's a practice where you have a dedicated infrastructure layer to facilitate service to service communication between microservices using a proxy. So what we exactly do out here is, if you look at the diagram out here, a service mesh has two different layers that it has: the control plane and the data plane. The control plane is where all the logics rely. So like I was talking about monitoring the outbound traffic, right? So I can tell the control plane that I want the traffic to go only to google.com and not yahoo.com. Or maybe something like, if a traffic is going to yahoo.com, you redirect it to google.com. So that is something that the service mesh can facilitate us. So I'll write all these rules in a control plane. I'll tell all the redirect rules that I want. If I want any circuit breaking and these kind of, so I'll write that in control plane. And what the control plane will do is, it'll deploy proxies. If you see on the data plane, we have proxies attached with all the services that we deployed. So service A and service B are two normal pods that you deployed. So it might be the web app and the REST server. And whenever you deploy the web app and the REST server, we'll automatically attach a proxy to it. So the proxy will be the one that will take in all the inbound requests as well as outbound requests. So if we want to reject all the traffic to REST server, we need not go to the code and do it. We can write the rules on the control plane itself, and the control plane will sync it to the proxy of REST server, and it'll take care of enforcing all these rules that you have. And you can see that the proxy is responsible for all the inbound and the outbound traffic. So suppose a REST server has a malicious code that is sending all your payload to, say, yahoo.com or maybe some other xyz.com. So we can have particular rules enforced in the proxy that will restrict all the traffic. So you can just whitelist, say, google.com or yahoo.com. So only traffic going to these domains will be allowed to go out from the REST server, and the rest of the traffic will be blocked, and we can be notified accordingly too. So we can look into that. So you can be very, very assured that whatever you are writing, whatever content that you're writing on QuillBot is not going anywhere. And because of the proxy, right, the proxy also facilitates mutual TLS communication. So just like the router example that Gaurav Sen gave, uh, if your REST server, like the backend server, needs to communicate with the front end server, or the front end server needs to communicate with the backend servers, they need to first identify each themselves. So the first the web app needs to identify itself as a web app using some certificates or something that the control plane takes care of, and the backend also needs to identify itself as a backend server before it can establish a communication. So even if I as a developer wanted to sniff all the traffic that's going between the web app and the REST server, since I do not have the certificates that they have, I cannot really identify myself as a web app server. So the REST server will automatically start rejecting all the calls that are sent to me, you know a third party client that's trying to connect. So that security is also enforced using the mesh. So now we are done with the architecture. So I'll just walk through all the architecture that we have out here. So now we have the user on the left hand side. The user tries to visit quillbot.com. It first hits the Cloudflare, where we do some computation on the edge. So basically, that would mean is the computation will be done at a server near you. If you are in Kolkata, the server might be in Mumbai. So all the computation will be done in Mumbai. Where do we decide what type of payload that you might want? So you might be a part of a various A by B experiments. You might see blue QuillBot, you might see yellow QuillBot. These types of rules are baked into the edge computing itself. So if say you are a part of A by B group where you'll see QuillBot in blue, right? If we have that payload, so what Cloudflare will do is Cloudflare will deliver the payload to you from the edge itself. Otherwise, your request will be sent to web app, the backend servers out there in the United States. So the traffic that will be going to the web app will be going through a single public IP. We have rules and guardrails on our public IP, like the load balancer out there, if this traffic is allowed or not, and like the backend and the web app contract that we have, the Cloudflare also needs to identify itself as Cloudflare before entering our cluster. So if that check passes, you can enter our cluster. It'll go to the web app. It'll fetch the content that it needs to fetch. It needs to get. So before that, you can see a green line on the web app container that's there. So that's basically the sidecar proxy that we were talking about earlier. You won't be exactly hitting the web app pod immediately. You'll first go to the sidecar proxy that you have. That would have all the rules that if you're authorized to hit web app or not. And if you are, then your request will be proxied to web app. And from there, the request will be sent back to the Cloudflare servers, where your request will be cached, and the actor will get back the page that it was talking about. Now coming back to the APIs, you'll hit the backend again through same public IP and same reverse proxy that we were talking about earlier, and the backend will send all your requests to a message queue. It'll cache all. It will not exactly cache. It'll send it to a message queue where all your requests will stay there for a particular moment if our ML models are scaling up or something. And our ML models, once they are ready to process, once the GPUs are free enough to process your request, it will take a text from the message queue. It will it will process it, and it will add back the request to a different channel where the backend server can listen to it and send it back to the actor. So yeah, that was the architecture of QuillBot in a pretty gist manner. We also have a lot of other things that we missed out there, like the databases that we have, the Kafka cluster that runs, and other tracking activities or analytics, real-time analytics that we do. So that was left out for maybe another talk. So, yep, that was it from my side. This was Ashish and my friend Siddharth. You can always reach out to us on the handles that we have out here. And if you want to work with us, you can visit quillbot.com/careers. Yeah, open to questions now.
Anyone having any questions can please raise their hand.
Cool, I guess. If you have any other questions, you can always send them my way on my LinkedIn or the handles provided there too. It's basically my Instagram handle. You can DM me there too. Always there on LinkedIn and on WhatsApp too. Available anywhere.
Thank you,
Yeah, guys.
Ashish and Siddharth. It was a wonderful session and it was a very insightful session, and many of them got to know about Docker and Kubernetes, which is a trending topic nowadays. And thank
Right.
you for telling. Thank you.
Thank you, guys.
Thank you,
Bye
guys.
bye.
Yeah.
Thank you.
Have a good day.
I'll
Bye.
meet soon. Yep.